In the physical world, data is chaotic. Analog electrical signals are erratic, constantly shifting, and bound by the laws of physics. But when we look at a modern digital dashboard, we see perfectly synchronized, instantly updating geometry. A raw physical sensor and a cloud database speak entirely different languages. If you try to connect them directly, the data stream simply shatters. They require a translation layer to function together. That translation layer is the virtual instrument, or VI. It acts as the integration nexus, intercepting raw electrical signals from the hardware and restructuring them into standard digital packets the cloud can actually read. But moving that data through the VI introduces a strict set of engineering hurdles. The system has to cross varying voltage levels, span vast physical distances, and bridge completely isolated software architectures without dropping a single bit. Solving this requires building a multi-layered communication architecture. We have to map the exact path the data takes, starting from the microscopic traces connecting internal microchips, all the way out to global Internet of Things networks. This means tracing the flow of information across three distinct boundaries: the internal silicon buses, the local industrial hardware networks, and finally, the lightweight cloud pipelines. In an industrial environment, the reach of a VI is determined by its interoperability, its specific capacity to translate local signals into a format the rest of the world can utilize. Before data reaches a screen, it has to move across a printed circuit board, traveling from a physical sensor node to a local microcontroller. This is internal communication. It is a strict, highly localized link that tethers the physical sensors and data acquisition hardware to the local computer. To make this connection, engineers often use the I2C protocol. I2C wires multiple sensor nodes to a single controller over short distances, operating at low transmission speeds. When the system requires rapid data transfer, we use SPI. SPI establishes a point-to-point link between specific chips, achieving much higher transmission speeds. Once the data clears the microcontroller, it hits a physical boundary. It has to exit the local microhardware and enter the processing computer. We bridge this gap using serial communication protoslides RS-232. This transmits continuous streams of binary data directly through the computer's COM ports. For higher data volumes, the standard shifts to USB communication. USB provides the high-speed, plug-and-play bandwidth required by complex commercial devices like digital oscilloscopes. These internal protocols guarantee high-fidelity physical connections. However, because they rely on direct electrical wiring, they mathematically cannot scale beyond a few meters. To scale further, we have to pull back from the isolated laboratory benchtop and look at the vast environment of an industrial factory floor. You cannot run a USB cable across a massive manufacturing plant. Overcoming this distance limitation requires standard Ethernet and TCP/IP networking architecture. In this environment, the VI is usually targeting a programmable logic controller, or PLC, the heavy-duty computer directly managing the industrial machinery. Consider a standard integration case. A LabVIEW VI sends a structured command packet over an Ethernet network to a PLC, instructing it to read a register. To ensure the PLC understands the command, the VI packages the data using the MODBUS protocol, a reliable standard built specifically for reading hardware registers. While MODBUS handles direct register control, highly complex networks use OPC UA to ensure strict interoperability across thousands of distinct devices throughout an entire facility. Using these protocols, the virtual instrument acts as a critical data source. It ingests the raw, localized PLC data and formats it into standardized streams for centralized SCADA monitoring systems. If these standardization layers did not exist, integrating legacy heavy machinery with modern tracking software would be computationally impossible. The external communication layer abandons the simplicity of direct copper wires. It trades that physical connection for network addressing, automating the entire facility. But modern systems rarely stop at the facility walls. The architecture must push past the local area network and ascend into the global cloud infrastructure. Remote integration relies on TCP/IP sockets operating within a strict client-server architecture. The server binds to an address, listens for a connection, and executes a loop to catch incoming data. Virtual instruments utilize these sockets to stream continuous data over the internet to remote Python servers. Those servers parse the incoming packets and permanently write the results into SQL databases. This introduces a new constraint. When dealing with remote, low-power Internet of Things sensors operating on high-latency networks, traditional web protocols like HTTP are simply too heavy. The industry solves this with MQTT. It is a highly lightweight publish-subscribe protocol engineered specifically for devices operating on unstable or slow Internet connections. For example, an ESP32 microcontroller reading a DHT22 environmental sensor in a remote field does not try to host a massive web server. Instead, the microcontroller wraps that temperature data in a tiny MQTT packet and bypasses local servers entirely, publishing it directly to a cloud visualization dashboard like Grafana. If we plot MQTT back on our protocol graph, it sits firmly in the middle for transmission speed, but its maximum physical distance scales to the limits of the global network. The cloud layer entirely removes geographic limitations. It takes highly localized hardware measurements and immediately converts them into globally accessible intelligence. Engineering a stable connection requires accounting for physical instability. Maintaining a synchronous, zero-loss communication stream across these networks is notoriously difficult. Systems inherently operate asynchronously. A sudden latency spike on the network will cause incoming data packets to arrive completely out of order or simply drop. To prevent data corruption, engineers enforce strict temporal synchronization. They install a real-time clock at the hardware level for absolute precision and use the network time protocol to align those timestamps perfectly across global servers. We also construct buffers to absorb network shock. By utilizing thread queues in Python or timed loops in LabVIEW, the system securely holds arriving data when the database lags before it is metered out at a steady rate. Even with perfect software buffering, the architecture remains vulnerable at the physical layer. Devices at different voltages will physically destroy each other if connected directly. Engineers install logic-level converters to step voltages up or down safely. High-speed data traveling over long wires is extremely fragile. It requires heavily shielded cables to block electromagnetic interference from altering the binary states. Understanding network protocols isn't enough. It must be paired with rigorous physical safeguards to survive realities of time delay, distance, and signal interference. We have now built the complete communication model. Data generates at the silicon level over I2C, flows into the PC through USB, routes across the factory floor via MODBUS, and ascends directly to the cloud through lightweight MQTT pipelines. The virtual instrument sits at the absolute center of this entire web. It is the persistent translator, actively formatting and rerouting data every time a physical or digital boundary is crossed. The objective of constructing this elaborate network is singular: to establish a closed, real-time loop between physical world measurements and highly automated digital control systems. Mastering these specific interconnections allows engineers to take an isolated, disconnected sensor and integrate it securely into a global intelligence grid. The capacity to communicate transforms a localized measurement into a functional component of a larger, intelligent architecture. In modern engineering, the true utility of a tool is determined by how effectively it shares what it knows. At the start of every data pipeline is a physical event: a drop in temperature, a spike in voltage, or a change in pressure. A sensor detects this shift, translating physical reality into a digital signal. To make that signal useful, we are going to build a 3-stage pipeline. Step 1 is extracting the raw data from the local hardware. Step 2 is securing it in a local database on your machine. Step 3 is broadcasting it live to a cloud platform so it can be monitored from anywhere. You need 3 basic components to build this. First, a simple physical sensor. Second, a PC running Python to handle the processing. And third, access to a cloud dashboard platform to visualize the final output. By connecting these 3 pieces, we bridge the gap between an isolated hardware instrument on a workbench and a globally accessible, scalable data system. We start at the physical layer, where the sensor connects to your processing board. The protocol you choose here dictates the speed and reliability of everything that follows. This chart categorizes communication protocols by speed and distance. In short-distance quadrants, I2C and SPI communicate between internal chips. For medium cable distances, UART and USB populate the chart, maintaining signal integrity over wires. Once the physical cable is plugged into the PC, software reads the incoming transmission. In Python, the PySerial library opens the COM port, capturing the continuous stream of raw ASCII text from the sensor. Matching the physical protocol to your actual distance and speed requirements ensures the data arrives intact. A mismatch creates hardware-level bottlenecks before the software even sees the data. Now that the hardware is passing data over the cable, we move entirely into the software environment on your PC. High-speed sensors transmit asynchronously. If your sensor sends thousands of readings per second, but your Python script is busy calculating, the incoming packets hit a busy port and vanish. This diagram illustrates buffer management using Python. Incoming data blocks fall into a buffer funnel at irregular speeds and emerge in a steady line. To fix processing delays, the Network Time Protocol stamps a precise timecode onto each block entering the system. With the data neatly buffered and timestamped, Python executes an SQL command to write each row into a local SQLite database. This creates a permanent, searchable record directly on your hard drive. If you were building this for a factory floor instead of a desk, you would swap out the simple SQL script and use MODBUS protocols to read and log heavy industrial data directly from a programmable logic controller, or PLC. Buffering the data and committing it to a local drive creates a failsafe. If the facility loses internet access, the sensor continues running, and the local PC continues logging. No data is lost. With the local vault secured, the final step is pushing the measurements out to the internet for remote monitoring. We use MQTT for this. It is a highly efficient, lightweight messaging protocol built specifically to move IoT data over low bandwidth connections. This flowchart outlines the publish and subscribe model. Instead of the sensor trying to talk to the end user directly, it publishes its data once to a central MQTT broker. The broker then distributes it to anyone who has subscribed. Here on the Cloud Dashboard Configuration panel, we link the system together. You enter the MQTT broker address, specify the port, and type in the exact topic subscription name the sensor is broadcasting under. This model decouples hardware from users. The broker handles the traffic, feeding 50 different live dashboards, while the local sensor rests. Translating this architecture from a clean diagram into physical reality means dealing with physics. You will encounter noise, latency, and logic errors. Here is how to fix them. If your precision control system is suffering from high latency and jitter, standard TCP is likely too slow. Switch the communication route to a faster, connectionless protocol like UDP. If software cannot read the hardware, check your voltages. A 5-volt sensor communicating with a 3.3-volt board requires a physical logic level converter between them. If your incoming ASCII text looks like scrambled garbage characters, you are dealing with electromagnetic interference. Replace your standard wiring with shielded cables to block the ambient noise. And to handle unexpected network drops, program watchdog timers and retry loops into your Python script. This forces the system to automatically attempt reconnection rather than simply crashing out. A resilient virtual instrument assumes the environment will fail. It relies on a hardened architecture to catch errors and keep data moving. We can now see the entire pipeline in action. When the physical temperature rises and the frost on our component rapidly melts, the sensor detects the thermal shift instantly. That measurement is caught by the Python thread, permanently logged into the local SQL database, and published via MQTT to the cloud, where a gauge on your remote dashboard immediately ticks upward. The logic powering this small-scale test is identical to heavy industry. By swapping out the basic temperature sensor for an industrial PLC, this exact same Python and MQTT structure can monitor an entire manufacturing line. Integrating hardware protocols, software buffers, and cloud brokers provides a complete architecture. Mastering these steps gives you the exact blueprint required for modern virtual instrument engineering.